Okay, we're now recording as before, and I will upload the recording afterwards. Hopefully you guys have been able to download that if you want, and I did upload the blank version of these notes about an hour ago. This is about the least mean squared. This chapter is about the least mean squared algorithm, and LMS is sort of the prototype for all supervised learning algorithms. And as you'll see when we get to backpropagation, is essentially the same mathematics as with many of these other ones. So although it's a very simple algorithm, I think it's worth spending a considerable amount of time to look at the mathematics of it. And I'm going to go over a little bit of what the book does and then go a little bit beyond that, reviewing some things that we did in the perceptron lecture as well. Obviously, the structure of this algorithm is very similar to the structure of the perceptron algorithm. One of the differences, of course, is that this does not have the nonlinearity at the output of it. As we'll see in future lectures, that nonlinearity does not actually change the mathematics as much as you'd think it would. There is Haykin starts with a review of unconstrained optimization. What's the difference between constrained and unconstrained optimization? If you have all of these things are generally based on cost functions, an unconstrained optimization problem is I might have a cost function like this. I start at some point. I'm just trying to find the minimum of it. A constrained optimization problem might be that I have the same cost function, but I want to find the minimum point that lies on this line, which would be about there, right? And so often a constrained optimization problem is you're trying to, it may be working along a single line, or it might be working in this half plane, but you're constrained in such a way where you can't actually get to the true minimum of the cost function because there's some additional constraint. We'll look at constrained optimization in future chapters, but the reason he's calling this unconstrained optimization is because there's no constraint on the optimization process. So we looked at a little bit of this before, but I'm gonna do this again, and we'll see this multiple times as we go through the course. But I think sometimes repetition is helpful here, and each time I'll try to expand on this a little bit. So we start with some kind of energy criterion, and let me apologize in advance for the fact that Haykin and I do not always agree on our choice of variable names. I'm using J as our cost function here. Haykin uses J for the Jacobian. I will try to keep that from getting confused as we go forward. So we have some kind of energy criterion J that we want to minimize, and we have control of parameters. So the point is that the energy function hopefully is in some way dependent upon the things that we have control over. There's lots of things we don't have control over, so we don't try to minimize those. And the basics of calculus, if J was a one-dimensional function, well, if W was one-dimensional, J is always a scalar. The cost or the value of something is always a scalar. But if W were a scalar, then you could just do standard calculus, right? How do we optimize something? You find the zeros of the derivative, and the difference between a minimum and a maximum, of course, is whether or not the second derivative is positive or negative, right? So that's a standard. And what we're doing here is we're just pulling that up into the multivariate domain. And again, those of you who, most of you have seen multivariate calculus, so this hopefully is just a review, but there's some terminology. So recognizing that in this case, J is a scalar, but the gradient, this is the gradient of J, is a vector. And the reason it's a vector is because even though J is a scalar, you have to take its derivative with respect to each component of the input, of the weights. Right? And so this then becomes a vector of the weights, and it is essentially the gradient. It will always point in the direction of steepest descent. So if J, we're looking down on J from the top, this is J of W, it will, the gradient vector evaluated at any point W will always point down the direction of steepest descent. Right? So the gradient, this space is the space of doubles, in this case W1, W2, and what I'm drawing is these vectors, which are the gradients, the delta, it's the gradient of J, which is a vector in those directions. And then those vectors, of course, create a vector field so that at any point I can evaluate the gradient direction evaluated at that value of W. And so these are And so if I wanted to get to the center of this point, I could just literally follow those little gradient vectors down, and that's what we call gradient descent. So there's a couple of features of the gradient. If you have the gradient of, it's a linear operator. If I have two different cost functions, the gradient of the sum of the cost function is the sum of the gradients. That's nice to know. That will occur sometimes if you have a situation where you might have two different cost functions, maybe nearby. Oh, excuse me. Stop that. Maybe near each other. Oh, wow, that's different. Let me go back to here. Maybe nearby in some way like that. And then you say, okay, what's the actual gradient at this point, right? Because one of them would be going, one is going this direction and one is going that direction. And the answer is there, it might actually be zero, right? The actual gradient, because it's going to be the sum of those. I don't know which way to go, right? Those kind of things. And so you can imagine that if you were to expand this out and this out, there's going to be points at which there's going to be overlaps, and you'll add the two. And so the gradient is the gradient of the sum of the cost functions, the sum of the gradients. It's linear. This is again going to be very important, because although we're used to thinking of functions as linear, you also want to think of these sort of operators. A gradient is an operator. You want to think of operators as being linear versus nonlinear. And we'll be talking a lot about operators and functionals as we move forward in this course. The second, so the gradient is a vector. If you take a scalar function, like J, a scalar cost function, output is a scalar, the gradient is a vector. The second derivative is a matrix, which is referred to as the Hessian, and involves the fact that you have to take the derivatives in every direction. So that, for instance, you take the derivative, the first derivative with respect to W1, the second derivative with respect to W2, and that gives you the Hessian function. And the Hessian function functions like a second derivative, but unlike when you have a single one-dimensional function, and you can sort of imagine if this is f of x, and that's f prime of x, and you imagine that the second derivative sort of represents the curvature at that point. The curvature can be different in every single different direction, right? You can have saddle points, you can have curvatures, and these things when you're dealing with a three-dimensional function. And so these curvatures happen in every single possible direction and all possible combinations of directions. The second derivatives themselves live on the diagonals here. And so those terms can give you a rough idea of what's going on. But again, there can be all these combined directions that happen. So that Hessian matrix becomes important, and that is used in the Newton method. Another thing that you can do is you can calculate the Jacobian, which you can think of as the derivative of one vector with respect to another. So this is essentially the derivative of the vector E with respect to the vector W. And is often written in this way, where E and W are vectors. And the point here is this is also a matrix, because you have to take the derivative of every component of E with respect to every component of W. And as you see here, the tradition is that the E indexes run down the column and the W indexes run across the row in this case. Whereas the Hessian is always going to be a symmetric matrix, of course, the Jacobian may not be. And you guys, people who've done mechanics are very familiar with Jacobians. They're it's the vector derivative of one thing with respect to another. And so this is commonly used when you're doing coordinate transformations, for instance. Okay. So, and I'll keep introducing more and more of the terminology as we go here. And let me see, I do see. Okay. So I'm noticing that there are some comments coming through here, so I'm just going to make sure that I can answer these as they go. All right. So Newton's method is based on the Taylor expansion, and what happens in Newton's method. Actually, well, before I do that, because I think the example here of these pictures shows the idea of following gradients down a gradient descent. So this is just steepest descent. And one of the things that the point that Haken's making here, and we'll come back to this later, is how far you go along the gradient matters. So in this case, if you go a very small amount along the gradient in each direction, you'll get a very smooth function. If you go a lot further along the gradient in each direction, you'll get a very jagged function, and you'll overshoot. Right at this point, he went sort of beyond where the gradient was, right, and walked into a completely different area of space. And so you've got a very non-smooth function. Nevertheless, gradient descent will work up to a point. If you went way out here, you might actually fail. So we'll come back to these ideas, but this is the concept that Huygens was talking about, gradient descent. Now, Newton's method is essentially a second order method. So it looks at the second derivatives here. That's why the Hessian is going to become important in the two-dimensional case. So in this case, you can do the Taylor expansion of any function f. This particular discussion and terminology I just took out of the Wikipedia page on Newton's method. So feel free to look these things up. I just thought it was a better description than Huygens. So what you do is you say, okay, here's our Taylor expansion, and now we're going to say, let's look at the derivative of the second order approximation. So this is the second order approximation f of x. Let's look at the derivative with respect to time of that. We're going to set it equal to 0, or derivative with respect to t, some variable. We're going to set that equal to 0 to find the extrema of this function. And so using the second order, plugging in the second order expansion here instead of the original function gives you that. And when we take the derivative of it, we get this. So if you're going to set that to 0, then you can find the minimum, or at least zeros. So this is the first derivative of the second order expansion, right? So zeros of that first derivative occur when the variable t is equal to the negative of f prime over f prime prime. Right? So that's fine, and that's just the one-dimensional case. And now you can imagine creating an algorithm, which you don't know at this point whether it'll work or not, but it seems like a reasonable idea to create an update rule where you just sort of add values of t to this in some sense, right? Now, why would you add value of t? T is supposed to be the right answer, right? But this is the right answer only for the second order of approximation. If f of x were, in fact, a second order polynomial, then then the Taylor expansion is exact, and this would be the exact solution, right? But in fact, it's usually not second order, and so this is an approximate solution, right? So what's missing here, of course, is you don't see anything that looks like a learning rate in this algorithm, but you can just do this, and it will sort of bounce around. It might bounce a little too far, it might bounce a little too close, but basically you're making a second order approximation to this function at each point. And it turns out this works. And in the multivariate case, what it looks like is, so if w is now a vector, delta w, which is the change at each point in time, is a vector. And the second derivative looks like the Hessian. It's inverse because it's on the bottom here. And the first derivative in the Wikipedia page, they use g for the where g here is the gradient function. Right. So this says you take the second order and you multiply it by the gradient. Now, what's the difference? So the only difference between this, if we did gradient descent, it would be delta w equals negative gradient of f, right? That's gradient descent. So all they've done is you just scaled it by this inverse of the Hessian. Now, if we were to think about what the Hessian actually does, remember I said the diagonals of the Hessian here. These diagonals are just the second derivatives in each direction, right? So what this says is you're going to move fastest along the parts that have the smallest second derivatives, right? It's the inverse of that. Suppose the Hessian were diagonal, right? If the Hessian were diagonal, then you're basically going to scale how much you move along each dimension by the inverse of the second derivatives. Right? So the bigger the second derivative, the smaller you're going to move. The smaller the second derivative, the bigger you're going to move. That actually kind of makes sense, right? If I have a function that's very shallow and another function that's very steep, and I'm trying to make sure I don't overshoot, right here I can move a lot further than I can here because I'm going to overshoot on the steep one, right? So the point is you can move faster where there's less curvature, and slower you want to move slower where there's more curvature because you're more likely to overshoot. So it kind of makes sense, right? And by doing that scaling, even if you were to, for instance, put a rate term in front of here, a gamma term in front of the h, you'll find that gamma can be bigger because this will compensate partly for your risk of overshooting. And it sort of scales each dimension, or how much you move in each dimension, by the relative, by the second derivative in that dimension. So for instance, you could easily have, in 2 dimensions, you could have something that is very shallow along a valley, but very steep sides to the valley. And if you're up here, you want to make sure that you don't bounce all the way to the other side of the valley. So you're going to go slowly if you're coming down from there. But once you get to the bottom of the valley, you might want to move more quickly because you're less likely to overshoot the final point, right? So that's worth knowing. Now, the downside of this, of course, is you have to know that Hessian. In fact, you have to Hessian. Remember, it changes. It changes. It's a function of h. It's a function of w, right? It's a function of the weights. So the Hessian, you have to be able to calculate this thing, which really, in general, requires knowing your function, knowing everything about your error function, right? And you might know something about the error function, and you might actually be given the Hessian of the error function or be able to calculate it or estimate it. And there are iterative algorithms that are able to estimate components of Hessian, and so that has been used in a variety of algorithms. The Gauss-Newton method is slightly different. So the Gauss-Newton method, it's important to recognize when it applies. This applies most frequently when the error itself is a vector, or when components of the error are vectors. So a typical thing that we might have is that the overall error, or in this case, overall cost, I don't want to use J here because remember, Haken's using J for the Jacobian, whereas I was using it before for the cost function. But suppose this is your error or your cost function would be better. So suppose that's your cost function is the sum of the errors along each individual dimension, where the little EIs are a lot of dimensions of the error, right? The sum of the squares of those things. So in that case, the Gauss-Newton method applies because essentially you're taking the Jacobian of the error, which is now a vector, against the Jacobian, the Jacobian is the derivative of the vector error or the vector cost with respect to the weights, right? So these things are both, so that's where you get a Jacobian matrix from that. Now, when would this occur in a neural network context? So the usual way that this happens is it's not that the errors, you could make the error the component. You could imagine it would be the sum of, the optimal yi minus y. It could be something like that, right? It could be the sum of the over that would be one form of error, right? Where these are, actually, you know what, I'm sorry, this is going to confuse things. Suppose that you have that you're trying to approximate a function y is approximate f of x, where y itself is a vector, right? So so that's going to be like y1 to yn is going to approximate f1 to fn of x, right? So it might be that, and then I might look at each one of these y1 minus f1 of x, and I might take the sum of the squares of those, right? And I'm sort of doing this component by component. That's one way in which you could do it. However, that's not what is commonly done here. What is commonly done is that you would, some noise going on outside, I apologize. What's commonly done is that you actually define the errors this way. So imagine that I have a bunch of examples of y. I have y1 to yn, but these are examples. And each one of those, I want to approximate W transpose times x1 to xn. Stop that, please. And these should be interpreted. Y could be vector, X could be vector, it doesn't matter. But the point is that these are examples, right? I've fed you a bunch of different examples. And what I want is I want all the examples to be as good as possible, right? So now the way to interpret this statement is that the error in each case is just the error on the individual examples. So that would be another situation where this would be used. And this is the more common usage of Gauss-Newton method, for instance, in statistics. Okay. So that said, that's what I mean by this error vector, is the vector of all of the errors for every single example. Excuse me 1 minute, I'm just going to close the door here. Things have gotten very noisy. I don't know if that's going to help or not. So, all right. So now what happens is now we create this, we use the Jacobian, and this equation here, which is the Gauss-Newton method, looks a lot like the Newton method itself, right? I mean, it looks like there's some sort of there's an inverse matrix here, and there's some kind of derivative matrix here, right? So it looks very, very similar structure to this, okay? So what are these two? It also looks very similar, interestingly, to, the y hat equals RYX, RXX inverse X, right? Which is the solution of linear systems, right? So it looks very similar to that as well. And these things should look similar because they should, realistically, they're trying to solve very similar problems. You should come up with similar answers. This term here is the pseudo inverse of this matrix, which is sometimes written using this little plus sign. Okay, that's defined. It's essentially the pseudo inverse. If you could find the inverse of dEdW, and I apologize, this is the D's there are the wrong kind of D, right? We mean partial derivatives here. We're not looking at differential forms. But this should be dEdW pseudo inverse, right? Pseudo inverse because there's nothing that says that dEdW is actually invertible. It doesn't have to be invertible. The pseudo inverse, when things aren't invertible, it generally means there's more than one inverse. And the pseudo inverse is the inverse that is the choice of inverse that always leads to the smallest, the answer with the smallest total mean squared power. Right? And so this is the pseudo inverse of that matrix. And the reason I'm saying that is because it's important to think about what's happening. If you think about just in some kind of general sense of I want to relate W to E, right? Usually it's going to be something that looks like dW dE over times E, right? I mean, if you think about, how just in general in a univariate case, right? There's going to be some scaling factor between them. If these were linear, if W were a linear function of E, you would take whatever that dW dE and you multiply by E. So if this were just a scalar linear, right? The problem is we don't have dW dE. What we actually have is dEdW, right? So what you'd really like to do, then again, back to assuming this is a scalar case, is I'm going to approximate by dEdW inverse times E, right? That would work. This is just if this were a linear case. I mean, suppose W equaled A times E, right? This would be a particularly reasonable thing, right? dEdW would be 1 over A. The inverse of that would be A. And I'm going to get out the right answer. Right? So that's what the form of this equation is, right? Which is I am basically saying I'm approximating delta W through the pseudo inverse to E, right? Except that I'm putting the negative because I want to go down the gradient, right? But again, that's why this looks the way it does. The Jacobian is the thing that sort of has this form, and it relates. It's how do I get from W to E? Now, why wouldn't you just do dW dE and be done with it? Well, if you can solve that, great. But usually you don't have that, right? Usually what you have is you have the error or the cost function is what's specified, and then I can calculate this Jacobian, and then I have to use that Jacobian. And so what the Gauss-Newton method says is, okay, we're going to use the Jacobian in the following way. The other way to think about it is dE dW here functions a little bit like the gradient, and then we kind of correct for its speed in that direction. But I prefer to think that what's going on here is a lot closer to using the pseudo inverse. And that's just to sort of understand what's going on. Now, if you were to figure out what does dE dW look like, what does this thing look like in the case where this is what the cost function is, right? Well, it's fairly straightforward, right? I can take the derivative of this expression here with respect to W, and I'm going to get out xi, right? I mean, again, I'm hand waving this. I'm not going to go through all the details of the proof, but you imagine if you do that, you're actually going to get out negative xi. But if I take dE dW, I'm going to get something like that looks like xi or negative xi, right? And so what then is this term dE dW transpose times dE dW? It's going to look like RXX. It's going to look like the autocorrelation of X, right? And I'm taking the inverse of the autocorrelation of X, right? And I'm multiplying, again, dE dW itself looks like X, so it kind of looks like the X there, right? And then I also have, E, I'm multiplying times E. What's E? It's that kind of error there, right? So what have we reconstructed here? Right? We have just reconstructed this is the gradient descent algorithm, right? This RXX here is the inverse of the autocorrelation function, it's going to behave a little bit like the Hessian at that point. So you've reconstructed the Newton method, approximately. And what you've also reconstructed is what we're going to get to is the least mean square algorithm, which is this, right? Because that's now the same thing. If I can get these both on the screen at the same time. It's the same thing with this scaling factor here that says I'm going to scale by the autocorrelation function of x. Again, wherever x has high variance, I move slowly. Where x has low variance, I move quickly, which makes sense, right? So, so again, these are, or the directions in which x has low variance, I move quickly. The directions in which x has high variance, I move slowly. Again, you get the same answer. You should get the same answer. These things aren't all that different from each other, right? We're descending gradients. They're not going to be that different. But I just want to go through that. Haken doesn't make that point as clearly as I would like, although he does go through a lot of the math of this. So I wanted to simplify that and run through it a little bit more. Now let's get to the least mean squares algorithm. Okay, so least mean square algorithm, it's referred to as the Widrow-Hopf algorithm. It's been rediscovered many times in many different situations. Widrow and Hopf wrote a paper in 1961. I believe they were working for the AT&T or Bell Labs at the time. And one of its first applications was actually echo cancellation in telephones, right? It's, you may be, this is probably less of an issue with modern cell technology, but was a significant issue on phones, which is that, you know, if you speak at this end of a phone wire and then it goes to somebody else who's listening, it's supposed to be an ear at the other end, and they say something and comes back, there's also a little reflection back of this. So there's always these echoes on the phone line. And what you would do is at this point here, before you hear it, you would listen on that phone line, and you'd take a bunch of points along that phone line. And so actually, I'm going to draw this slightly differently. So you've got your outgoing, and I say something here. I'm going to take a bunch of points on that. And I'm going to say, can I predict what I'm going to hear from something I said a little while ago, right? And if I can, it means that those things came around and came back here. So it was a prediction problem. It was just and it's a linear echo cancellation, because you predict what you're going to hear here, and then you just subtract it. Right? And so the idea is if I can predict what's coming into my ear from something I recently said, then that means it's an echo. And you have to figure out what the delay is on that echo. But the delays were reasonably short. It's, you know, before we had satellites, the maximum delay was the amount of time it could take a signal to travel around the Earth. So it's reasonably small delays. And so with a fairly straightforward tap delay line, you could do this. And this was implemented essentially in all analog telephones. And some version of this exists in all communication devices as echo cancellation. Interestingly, it also, you know, fun fact, it also exists in your head. You have to cancel out the sound of your own speech. The sound for all of us, not just politicians, the loudest sound in our heads is our own voice. And you cannot necessarily, you would not be able to hear anything else unless you canceled out your own voice. And in fact, there are reflexes in your head, which mean that it make it such that if you hear certain types of sounds, it will actually, they cause vocal reflexes. And it's thought that one of the problems that happens in stuttering is that there is lack of cancellation of the sound of your own voice in your head. So you inadequately predict the sound that your own voice is going to make in your own ears. And so what happens is, because of that incorrect prediction, there's sort of a stop signal that comes in and says, hey, you know, I thought I said this, I actually said something else, something's gone wrong, stop. And that's what causes the stopping and stuttering. And from those of you who've seen the movie The King's Speech demonstrated this, you can, by changing the delays in the feedback loop for sound, you can eliminate stuttering. So someone who stutters, if you play them back their own voice through headphones at some delay, it will actually stop the stuttering, because it basically it changes the delay on this feedback loop and essentially fixes the feedback loop. Probably because it's not that the feedback loop is broken, it just can't operate quite as fast as it needs to. Anyway, as the Widrow-Hopf algorithm, it's everywhere as echo cancellation in both linear and nonlinear forms. So it's important to realize and this gets confused a lot when people see proofs, and I think this is probably obvious to people, but I want to make it very, very explicit. The Woodrow-Hoff algorithm, as stated here, takes examples of xi and yi, or usually you should think of x of t and y of t, right? These things are coming in at points in time, and you're seeing them in points of time, and it will adapt these weights just based on this, right? There's nothing else coming in, and contrast that to the Gauss-Newton method or the Newton method, where you need to know these Hessians and Jacobians of the cost function, right? The cost function doesn't enter here. It's implicit in the Woodrow-Hoff algorithm. You don't see the cost function. You never have to know the cost function, right? It's not, there's an implicit cost function, but you don't know it. And you don't know where the zeros of that cost function are. You don't know the Hessian of this thing. You don't know the Jacobians. You don't know anything. All you get are these values of x and y. And that's the brilliance of this. And I'll come back to how that works. But it's important to distinguish that use, which is the ultimate use in, well, there's many uses in machine learning. This is sort of online recursive use. I'm seeing examples one at a time, and I need to learn from those examples one at a time. So this is the situation where I'm seeing examples one at a time come in, and I need to do something with them. There's another way you could do it, is you could accumulate examples for a while, right? You could say, okay, I've got a bunch of examples. I'm gonna take the next 1,000 examples, remember them, and then I'm going to learn from all of those at the same time, which is fairly straightforward because you could just add them up like this, right? So I could just do this very quickly all at once. There are the idea of, there's a class of algorithms called wake-sleep algorithms that work partly on this concept, where you store a lot of data while you're awake, and when you're asleep you do a lot of learning. That's probably more relevant to unsupervised learning. That probably is a lot of what happens during wake-sleep cycles for humans. And but in fact, that's been successfully mimicked in certain classes of network algorithms. But it's important to recognize the difference between these sort of batch algorithms, which at its simplest is just doing learning in a batch, and these sort of single sample online algorithms. So when we analyze these things and we try to look at these, x and y are random variables, right? Somebody handed to them. So from our point of view, these things look random. Now, they have to be drawn in some sense, like any random number, it has to be drawn so that you go down the gradient. What does that mean? Well, suppose that, I'm trying to descend. So I've got a cost function, and I'm here, and that's where my gradient is, right? But suppose that I don't draw samples that sort of give me, how am I going to know that that's the gradient, right? The reason that's the gradient, this is the average gradient, but remember, I just got single samples of x and y. Any given sample, y minus w transpose x, might have pointed in that direction or that direction or that direction, right? If I take enough of them and I average those, I'm going to get this. But any single sample might have pointed in the wrong direction. Now, they don't always go in the right direction. It's just average, right? Because even when you solve this problem, even when you get to the solution, maybe there is no linear solution. As you guys saw in the homework, you can come up with problems for which there is no linear solution, right? And what's going to happen is these things kind of bounce around, because sometimes, one particular pair of y and x might actually give you the wrong direction, just because on average the voting is going to be such that everybody else is going to go in the right direction, but they could be wrong, right? But suppose that I only picked values that went in the wrong direction, right? As I'm handing you these random samples. Well, now my average gradient is going to point in the wrong direction. I'm going to go up the gradient, right? So the fact that you get to gradient descent means that you randomly sample so that on average you're going down the gradient. Because when we draw this as if we start at a point, we make these nice little gradient descents in like that, that's not really what happens. That's what would happen if you knew the gradient and you perform the Newton method or you did a batch thing. What actually happens is you get one sample goes here, one goes there, one goes there, and they're kind of bouncing around in all sorts of different directions. But on average, you will get where you need to go. That's the brilliance of the Woodrow-Hoff algorithm, right? Which is on average it will work. So you can look at the conditions under which those averages do the right thing. So let's look at the average change. Let's look at the expected value of the change in weight, and let's see where it goes. So expected value of the change in the weight, we just take the expected value of both sides. Now, here's a trick with the expected values, right? X and Y are random variables, right? Delta W is changing based on X and Y. So technically W is also a random variable, right? Because it depends on the values of these random variables, past values. Generally what we do is we assume, though, for the purposes of computation, that at any given moment, W is not a random variable. W is a thing that we are trying to change. So it's not random because essentially we're changing it. This delta W is sort of our choice. And that we have some sense of, in some sense, there's free will over your ability to push the weights where you want them to go. You don't have free will over the choices of samples you're given, but you do have choice. So that expression of free will, or that expression of the fact that W is the manipulated variable, means that we don't treat W as a random variable in this. But there are circumstances under which you do want to treat W as a random variable. So we'll look at that as it happens. But here, when I calculate this, you'll notice that I did not treat W as a random variable, right? When I take the expectations, I take W outside. Remember, expectation is a linear operator, just the way gradients are linear operators, which means I can take constants outside the operator. All right. And so the expected value of yx is ryx, the expected value of x, that's the autocorrelation of x. And you find, and now again, if I set this to 0, and what I'm doing is I'm saying, when does W stop moving? Right? What are the null points of this vector field? When does delta W stop moving? On average, it's going to be when Rxx inversed Ryx, right? Good, because we knew this anyway, right? Remember, this was, again, the solution to, actually, I wrote that backward, but it should be, let me write that forward. This is the linear Ryx, Rxx inverse x, right? That's the best linear approximation of y from x, right? So you see these same things keep coming up over and over and over again. You're going to see this kind of term showing up over and over again. Whether the x appears on this side or over here depends on how I put the transposes, whether I get the transposes right. So here again, we get W star is equal to that. But look at this Rxx inverse term, right? So we're trying to invert a matrix. What happens if that matrix is not invertible and has low rank? Well, then you can't do it. Yes, you could use a pseudo inverse, but the point is that what it would mean is that you're losing information. So what this essentially means is, suppose that for some reason Rxx was low rank, and in that might be the situation where let's say we're trying to converge like this. I start from a point here, and I only give values of x that lie along a line, right? Or somehow I only, I'm just, I'm never going to get anywhere else, right? This is not an exact, right? It's not exactly what would happen, but imagine that this is low rank in the sense that the x's are drawn from this distribution. The reason I say it's not exact is this is actually the W space, not the X space. But in the X space, suppose I only drew them from along a single line, right? Now, W transpose X, if X only lies on a line, this thing also will only lie on a line. So essentially, I can only explore one line in the W space. And I might be able to minimize along that line, but I will never minimize perpendicular to that line. And that's what will happen, is you will find a 0 of this. The weights will stop moving, but it will not actually be a minimum of the cost function. Right? And that will happen if essentially you can't even calculate this Rxx inverse, but you can still do the algorithm, right? The algorithm does not require any inversion of matrices. So you can run the algorithm. But the problem is, what you'll find is that if you try to look at what his convergence point was, you're not going to get to this. You're not going to get the right answer here. And if you use the pseudo inverse, you'd find that you end up at a point that is close to, and in some cases, the minimum distance from the optimal, but is constrained to be on that line. This is related to constrained optimization, right? It's one way of doing constraints, but it's not the right way. So the idea here is that you really want to make sure that X is being drawn from this sort of a random distribution. Otherwise, you're not going to get to the right spot. Now, for people in control theory, and again, I'll probably come back to this at various points in the future, there's this concept of persistence of excitation. And adaptive control is very much is where this comes from. And I don't know if we'll get to it in this course, but the basic algorithm for adaptive control uses something very similar to Woodrow-Hoff to adjust parameters in a control architecture that will optimize a cost function on the controller. Right? So this is often a performance function for a robot where there may be a series of parameters that need to be tuned in some way. And there you have this concept of persistence of excitation. Now, in that case, it's the same kind of thing. The idea is you need to explore the space. If I'm trying to get a robot to, walk along the sidewalk, and then all of a sudden it steps off the sidewalk and it's on a beach, it may not be able to walk on the beach because it never saw data drawn from that environment, right? So it could walk on the sidewalk because it saw data drawn from that environment. So the idea is that you need to show if you're going to train something, you need to show it examples of everything it needs to know. But it also needs to be persistent, because if you do a recursive algorithm like this, and all my recent examples were from sidewalks, even though I might have learned how to walk on a beach last month, I'm going to gradually change my weights to be better and better at sidewalks. That's not necessarily a bad thing. It might mean, hey, I'm never going back to the beach, and why waste bits on that representation? But if you want to be able to walk on the sidewalk and the beach, you have to go back and forth. And for this class of algorithms, when applied in a robotics context, you need to be able to go back and forth. And that's the concept of persistence of excitation. When you look at just the statistics, this is where it shows up. Persistence of excitations over the X domain, right? It's X is sort of the input, Y is the output. You need to persistently excite the input so that you see the Ys that are related to all the inputs you care about. Or you can say, I really don't care about that. I don't need to persistently excite that. Let's reduce the amount of data coming from unimportant areas of the input space, right? And you want to be very thoughtful about this, because algorithms can perform very well or very badly. If you train something on an area that you don't care about, it may spend a lot of time trying to approximate something you really don't care about, whereas you might be able to find that had you not done that, things would have been much, much easier. An example I like to give is there is this idea of suppose you're trying to train a facial recognition thing, right? And you're trying to train facial recognition, and you are showing lots of different faces, and you're trying to get it to tell you if somebody that it sees is your grandmother or not, right? And that problem, whether it's hard or easy, depends entirely on whether your grandmother is the only person with white hair in the images. Because if she's the only person with white hair, the classification problem is very, very easy. As soon as a second person with white hair is shown, the classification problem becomes very, very hard, right? So the X domain and choice of the variables in the X domain and what area they span within that domain can change a hard problem to an easy problem, or vice versa. Or it could end up just solving the wrong problem entirely. Anyway, so I wanted to show that aspect of these things. Now, let's back up here. So far, what I looked at here is I just looked at sort of what's the equilibrium point of that equation. We did some of the LMS equation. What's the on average equilibrium point? When do I expect the expected value of delta W to be 0, which basically just means that it's bouncing around near the equilibrium point, right? That it's in general stays that, right? The expected value of delta W, so it's as likely to move left as it is to move right, okay? But what you really want to know is, does it actually converge to the equilibrium point, and does it get there in some sense? Because just because this is an equilibrium point doesn't mean you'll find it. Right? Imagine, and people talk about this as being the problem of local minima. Make some space here. Imagine that you had a sum of two cost functions that looked like this. And I want to get to this point, but I start here, right? I'm going to descend into that one, right? So just because, and at this point, delta W will be equal to 0, but it's not the minimum. This thing could be the global minimum. So at this point, delta W would have been 0, 2, and if I'd started here, maybe I would have found that. But depending on where I started, I might get to one minimum or the other. They're both minima. So the question is, do you get to the right minimum? And can you get there at all? The other way in which you can run into problems with getting to minima is if the rates essentially go to 0. So suppose your cost function goes like this, right? And maybe the minimum is there, but it's just incredibly gradual here. This could be very, very slow going along that, right? Because the gradients here are tiny. Gradient here is very big, but now you're along this valley, and you just, the bowl just starts rolling incredibly slowly to the point, and you can create sort of Zeno's paradox kind of things where the ball will never actually get there. So, so what are the circumstances under which that happens? Now, I mentioned before, I think in the 2 lectures ago, about the this Liang result from 1977, which is important. This is not the only example of this type of approximation, but it's important to realize that this exists, and this is one of the ones that has the broadest applicability. It's different, for instance, I think in the chapter he talks about this Kushner approximation, which is a more restrictive version of the Liang criteria. So I prefer to use the Liang criteria, but you can see that the Kushner approximation is similar. So what they're talking about is under what circumstances does a stochastic difference equation here, being driven in this case by something that is a random variable, right? These are the E's, but really E should be, Y and X, right? So these are driven. So this is a stochastic difference equation, right? So we're making small finite changes in response to observations of random variables. Under what circumstances can that be approximated by a differential equation? And what you mean by approximated is, do they get to the same point? So again, I can have my stochastic differential equation is doing this. It's bouncing around as I see lots of examples, and maybe it goes to some point. And I might have a differential equation. I'll use a different color for this. I might have a differential equation starting at the same point that kind of does that. And it also goes to the same point. So there's a couple of questions that I might want to ask about this. One of which is, do they go to the same point, same answer? And do they get there the same way? Right? Because you could say, what's the difference? How far from the differential equation path does the difference equation go? Right? And you want these things to be bounded in some way. So what you'd really like is that over time, these things kind of zoom in a little bit. Right, so that unlike the way I drew it here, let me draw that slightly differently. So unlike the way I drew that here, so that the difference equation, even though it's bouncing around in here, ends up going down and going to exactly the same spot as the differential equation, like that, and getting closer and closer in some bounded way. Right, and people who want to read the Liang article, I think I uploaded it. It's probably on the materials that are uploaded on the site. There's certainly a lot of math in it, but it's important to recognize what happens and how he actually does this. So for people who are interested in differential equations, it's definitely worth looking at that. There are some criteria that are required for this. So the way this works is you take a stochastic differential equation. This is just the way that Liang wrote it, which has a learning rate. It's got some function which depends on the weights and depends on some random variables. Right as E, but think of E as the combination of Y and X. It doesn't have to just depend on the error. It can depend on Y and X themselves as the LMS equation, as the LMS rule actually does. So for instance, in this case, E might be driven by an error, but it doesn't have to be error driven. So now what the differential equation looks like is the expected value over X and Y, or over E, of this right side. So the point is that you have a stochastic differential equation that's behaving like its own expected value at each point in time. And remember, that's what I was saying. You have all the little, every time you get an example, the weights could drive you in the wrong direction, but on average, you follow the gradient, right? So this is the point, is when is that true? When, on average, do you follow this average behavior? When, right? Because and in general, the reason you care about this is it turns out that the differential equations are almost always easier to solve. It's the math is almost always easier, and you'll see that because the proofs that Haken does, which often use the difference equations, tend to be quite complicated, right? He's using all sorts of approximations, right? Whereas when you do differential equations, often 2 lines you can make the proof. So the criteria, and we went through these things before, but I just want to be clear about what these are. So we look at criteria number 1, the input data, right? E of t, which is, again, think of that as X and Y. They're independent, bounded, and they depend smoothly in some sense on each other. or on the underlying variables that you care about. So independent means they have to be drawn independently. You can't draw them in some you can't draw them to be dependent on each other in some way. You can't be malicious about it. They have to be bounded, so you don't want, can't get infinity, or things that go to infinity. And in some sense, they have to smoothly depend on X and Y. And you can imagine why all that would be true. Like any failure of those things would be an issue. Again, keep in mind that that is almost always violated when you're dealing with time-dependent data. So just as an aside, when you look at the, get a mess here, I'm going to get rid of all this extra stuff there. When you look at the LMS rule here, X and Y are not necessarily just examples drawn off the internet, right? The X and Y could be a time series, right? I could be handing you, X could be a time series of data. I'm handing you a local temperature measurements, and Y could be, tomorrow's temperature, right? And it could be just a sequence of daily temperature measurements and predictions of temperature. It could be the telephone example, echo cancellation. These things could be happening in order, right? In which case the X's are very related to each other, right? XT plus 1 may be related to X of T through some smooth function, right? Or through some filter. And similarly, Y of T plus 1 will be related to it. So in fact, this requirement of true independence is often violated when you're dealing with time series data. Fortunately, it doesn't matter that much, but it's the same kind of thing. If you're trying to walk on the beach, or you're trying to walk on the sidewalk, when you're on a beach for a little while. Now you're on a sidewalk for a little while. You may go back to the beach, but your last step and your next step are probably drawn from the same distribution, which means these are not independent samples, which means you're not guaranteed to converge under the Leung criteria. Unless you have to muck with it a little bit. Again, you can use persistence of expectation, you can use different kinds of sampling things, but just as written in its raw form, you have to be aware of that. Okay. Q, which in this case is this function has to be continuously differentiable. Okay, that's fine. And that just has to do with the fact that, you're calculating derivatives. And you can imagine derivatives are going to happen in various places. But you can imagine lots of situations where Q is not differentiable. The perceptron, for example. Right? If Q is a binary output function, that's not differentiable even once. Certainly not continuously differentiable, and so it has no derivative, let alone a continuous derivative, and so there are going to be lots of situations where it's not. Another interesting one that is not continuously differentiable, of course, is the what are called the half adders, so the ReLU units, I'm just blanking on the name, but the standard units that are used now in lots of the neural networks will look like this, and will just be linear up like that, right? And so at 0, they don't have they're obviously not differentiable, right? Which is a huge problem. And so people will do things to make them differentiable. They'll smooth it out at that point. It's not necessarily going to that can fix the problem, but you have to do something, right? You have to do something to fix it. So the continuous differentiability of that is going to be important. The expected needs to be bounded as T goes to infinity. Okay, that's fine. You can imagine why that, again, things, you don't want these things just blowing up, and blowing up is usually the thing that goes wrong with a variety of network algorithms. And the most important one that we pay attention to is the learning rate. So this gamma, which has to go to 0, not too fast and not too slow. Why does it have to go to 0? Back here, if the learning rate doesn't go to 0, you'll still bounce around forever, maybe in some small area, but you still bounce around forever, right? The differential equation won't bounce around forever. The differential equation is going to converge to some point, because that's what they do, right? Unless I added noise to this somehow, it's going to stop, right? Or go to infinity. Those are really its only choices. I guess it could circle, but it's certainly not going to bounce around in a small region randomly like that, right? So that's the point, is you need the rate to go to 0. Otherwise, you're not going to basically choke off the bouncing at some point, right? Let me go back here just because the name, the rectified linear units, I apologize. Get that name there, rectified linear units. Anyway, so the rate needs to go, it needs to go to 0. However, you don't want it to go to 0 too slow, because if it goes to 0 too slow, now what's going to happen is this is going to do that, and it's basically going to go to 0 here. Maybe it gets 0 there, right? But if your the differential equation might not have converged until you got, give me a break here. This thing gets stuck on me. Oops, I don't know what happened. My pen fails. This if the differential equation doesn't stop till here, but your rate went to 0 there, or basically, again, like a Zeno's paradox, it went to 0 fast enough that it'll never get there, right? I go halfway, I go 3/4 of the way, I go a little bit more, and I'm just never going to get past that point. Then I also won't converge to the right answer, right? So for that, I need that the integral over time of the gammas is infinity, right? So in other words, I never stop moving. It's not that gamma is not equal to 0. It's that there's enough area, there's always area under the gamma curve. There's always essentially infinite area under the gamma curve, so it can always get there. But if gamma is too big, it's going to bounce all over the place. So now I also need to limit gamma so that to some power, it's less than infinity. And then you need this kind of criteria with the gammas in some sense are smooth. So gamma is allowed to bounce around, but it can't bounce around much. It has to be smooth over time. Very typically, people will set gamma of t equals 1 over t, which satisfies these. Right? So that will satisfy all of those criteria. And that's one of the reasons that people do it. Use 1 over t. 1 over t squared does not, right? 1 over t squared, for instance, the sum of gamma t is not equal to infinity if you use 1 over t squared. It's not going to be true, right? So you have to, but again, you have to, so there's a lot of different, so that would be a case of it being too fast. And if you just use gamma some, if you just set gamma equal to some finite value, let's just say, gamma equals epsilon, where epsilon is very small, then you have, the sum of epsilon to the p value is not less than infinity for any finite epsilon, right? So this is how the Lyoung criteria actually tell you what you're allowed to do with learning rates. Now that said, that's not exactly what we do with learning rates, because this is all under the circumstance that you want you want the differential equation and the difference equation to converge to the same point. And maybe you don't care that much, or maybe you're willing to say, okay, it's all right to bounce around a little bit in that area, as long as we stay close to that area. Okay, so that could be all right. That's not what Lyoung says, right? Because you could have asked for a criterion such that the limit, make this. The limit as t goes to infinity of say the differential equation, let's say let's call that f of I get this thing right. Limit as t goes to infinity of w by the differential equation minus w by the difference equation. You might want that thing to be less than some epsilon, right? So you could say, okay, I just want to keep it close. That might have been another. That's not Lyoung's criteria. He wants this thing to go to 0, so that so that's why these criteria are important. Okay, but if you do that and you solve that, now you can approximate solutions to the stochastic difference equation using the ordinary differential equation, which allows you to figure out, do you actually get there? Remember, it's not just this, it's not just good enough to just say, do we have the same answer? When is delta W equals 0, right? When do we stop bouncing around? You have to say, can we actually get to that point? And so here, now this is the ordinary differential equation, right? This is the expected value of this. We already knew that because we've already calculated it a couple times along the way, right? But this is a differential equation, right? There's a difference equation. So now I have a differential equation. And in this case, note there's no gamma in the differential equation. The gamma is just in the difference equation. I could put a time constant on here if I wanted to, but you don't have to. So, and also this doesn't say anything about how long it takes, right? It doesn't say which one converges faster, because time it's hard to compare time in these things, right? Your time is an arbitrary constant, but you can ask the question, not using this technology, but you can ask the question when, what's the equivalent time constant, or what would this look like if we use smaller step sizes? Because of course, any real differential equation is going to be calculated using finite time steps. So you could look at those. Anyway, that's not what's happening here. So now we're going, let's do this. And this is now a different proof than I did 2 classes ago, because I'm going to do this entirely in the ordinary differential equation domain, right? So this thing is a stochastic difference equation, and this thing is an ordinary differential equation, okay? So let's again look at the cost function. Okay, here, so this is a standard cost function, right? This is the true y's minus the approximation squared. But let's just look at what's that expect. Let's write out the expectation of that. So I can write it out. It's so J is equal to this. This is my expected cost over time. Right? And it involves W's, of course. And so I can look at the change with time, dj dt. And what I really want to show is I want dj dt to be less than 0, right? If the cost is always decreasing, and I know that the steady state is at the minimum of the cost, then I'm done. Right? This is Lyapunov theory for convergence, right? It's you have the J because the cost becomes a Lyapunov equation or Lyapunov function for this differential equation. Okay. So I'm going to say, what's the change with time? So dj dt is dj dw times dw dt, just chain rule of differentiation. So let's look at those 2 forms. dj dw is this, just coming straight off of that. I can just derive with respect to w. And again, I'm playing fast and loose with the terminology here and throwing transposes around, but it comes out to that. And now let's insert the ordinary differential equation here from that, which we knew was that. And now if we take the product of these 2, it's always less than 0, right? One of these is negative of the other, right? This thing is the negative of that. And so now when I take the product of them, I get the negative of this thing squared, which is always less than or equal to 0. So that's the proof. So that allows us to prove that what we've basically shown is that the stochastic differential equation will stay close to the trajectories of an ordinary, the stochastic difference equation will stay close to the trajectories of an ordinary differential equation that is guaranteed to reduce the cost. So that means that the stochastic difference equation will reduce the cost over time. Now we've shown that in other ways, right? You can actually show that the single single step the single step actions of the averaged equation will decrease this. But like again, going back to what's the hard part here? The hard part here is y and x are drawn from they're random variables drawn from a distribution that you don't see. They will not always point down the gradient. But we've proven that if you can satisfy the Lyoung criteria, right, and if you can do that, then this equation, even with these things pointing in little random directions, will actually end up decreasing the cost. This is actually a big deal. Stochastic differential equations or stochastic difference equations are hard to deal with, right? And so the point is, it says that you will get to the right answer eventually if you can keep your learning rates low enough, right? And again, there's a few other things that have to happen in there that are sort of hidden in all of this. As I said, remember, RxX has to be full rank. If RxX is not full rank, then you'll find that this is always true, but you may not converge to the right place, right? J will continually decrease, but it could stop not at the right place. So the Lyapunov criteria is that there has to be a unique minimum. And if RxX is not 0, the minimum is not unique, right? So that there's some hidden things in there that are important. So if there's a unique minimum and you're always going downhill, you will hit the unique minimum. If there's not a unique minimum, I can at least show you're always going downhill, but you might not get to the unique minimum. Well, there isn't one. You might get to any one of a number of different minima. And sometimes that's good enough. Okay. We've talked about this issue of how you derive learning rules from this, and we've done that before. But the basic concept here is in the multivariate domain is if you set dj dt equal to the gradient of j. Well, dj dt is equal to gradient of j times w dot. What you want is you want this to be less than 0. And you can always do that by setting w dot equal to the negative gradient. That's why gradient descent works. We've talked about this before, but I just want to say that again using this terminology. So if w dot is negative the gradient, and that's all we've done here, right? Is that we have it just turns out that w dot is the negative gradient. Again, in the ordinary differential equation form of it. That gives the average solution. Now, you'd say, okay, fine, we're done. I can now find neural network learning algorithms for any cost function, right? Give me any cost function. If I can figure out its gradient, I can now set this, and now I'm going to be able to send that gradient. Here's the problem. You don't always know the full cost function, right? In the sense that, I might have examples, but I might not actually know that function, right? I don't know the cost function that specifies what is a picture of my grandmother and what isn't, right? I might have examples, but I can't write this down in closed form. That's one problem. The other problem is you want this to be data-driven, right? You want individual data sets to come in, whereas this w dot equals negative gradient of j, as written here, for instance, if you look at what this, well, let's go back to here. If you look at this is not driven by examples. Right? This is driven by knowing these two correlation functions. Now I could get those correlation functions. So that's what we call a batch algorithm. I could observe lots of values of x. I could calculate rxx. I could observe lots of values of y, and I could calculate ryx. And then I could do this. In fact, it would be even faster just to invert it, right? I could just do my usual, so if I had a non-data driven algorithm like this, I could just calculate this directly using, my usual rxx inverse ryx, right? And that would give me, say if I set w equal to that, I'm done. So I don't need to use an algorithm to do it, but this algorithm will converge to that answer. Right? So you could do that, but it just wouldn't be particularly efficient. But that's a batch algorithm. But again, we're also interested in these online algorithms. There's differences. Just going back to here, pure gradient descent does this, but pure gradient descent is only one way to descend a gradient. You don't have to go straight downhill, right? Anybody who skis knows that going downhill while being fast is not necessarily the safest solution. And so there's many ways to get down a hill. All you have to do, the requirement is just the dot product has to be less than 0. So on average, you have to be going down the hill. Again, think of skiing. You're always going down. You're not going to go up the hill, but you may not be going down the gradient. You may not be going down the steepest point. You go left, right, you bounce back and forth, right? That's fine. That'll still get you down the hill. There's lots of ways down a hill. The Newton method and Gauss-Newton are different ways of pointing down the hill. They're still going down the hill. So this is only one way to make sure you're going down a hill. There's lots of ways to do that. There's lots of ways not to do it. So you got to be sure that you get the right one. What you want to think about is that if you're handed a gradient, if you're handed a cost function like j, and you can calculate its gradient, maybe in a few special cases, your goal then is to invert this whole process. So your goal then might be to say, back to the Leong equation, somebody's handed me a cost function j. I'm going to set w dot equal to the negative gradient of the cost function. Can I find a stochastic difference equation for which this is the averaged behavior? And that's one of the ways in which you can find neural network algorithms based on cost functions. Right? You can't always do this. You don't always have the cost function. You can't always calculate its gradient. But in circumstances in which you do, or you have a class of cost functions for which you know the gradient, you can go back the other way, right? I'm showing you how do you go from an algorithm. Woodrow Hoff told you, here's the algorithm, how do we prove it converges? But suppose you want to go the other way. I know I have a cost function. I want to descend its gradient. Can I find a stochastic difference equation that averages to the right answer? Okay. And it's worth thinking about that. If I can come up with some examples, I will, but we'll talk about this again more in the context of different algorithms. I want to lay the groundwork for all of these things. Now, I talked a little bit about the learning rates, that for the Leong approximation, generally you'll may have the rate decreasing. Usually people just choose 1 over t, but the problem with 1 over t is that it converges, right? It makes the assumption that your function is fixed, that y equals f of x is fixed. And I get lots of examples of x and y, and eventually I get to the right answer. But what if y is changing, right? So what if, X is coming in, but Y is changing a bit, right? It's like, the weather last week is not the same as the weather this week. My predictions are changing. I'm just trying to predict a different thing. I added a weight to the edge of the robot. I put headphones on my ears. I'm listening with, there's a different environment. There's noise in the environment, different qualities of noise. What if it's a changing picture? That's one of the reasons to use constant learning rates. If you use a constant learning rate, it will listen to, it never stops listening. It never stops learning. It's always learning relatively slowly, but it never stops learning. And in fact, recent data has the ability to kind of drown out data long in the past. What does the learning rate actually do? Well, let's look at this. Let's look at the batch algorithm learning rate here. So this is the batch algorithm learning rate. If W is one-dimensional, RYX and RXX are both constants. So in this case, I suppose I just call this RYX of t. Let's just call that a constant function of t, f of t, but maybe it's changing with time, right? And I'm just going to assume RXX is equal to 1 for the moment. So this looks like a differential equation of this form. It's a very simple differential equation. And again, that equation, if we wrote it as a filter, so I can Laplace transform both sides of that thing, and I come up with the following filter, which is a low-pass filter, right? And the Bode plots of this thing are going to look like, it's it always starts at 1, but depending on the value of the learning rate, it might look like that, or it might look like that, right? So these are different values of gamma. So the point is how much. So if gamma is very big, right, what will happen is that I'm going to learn, I will pay attention to high frequency components. I'm going to learn a lot of stuff that's coming in fast, right? Learn right away, but I'm going to forget the past faster, but I'm going to learn things very quickly. If gamma is very small, I will only learn things over long periods of time. So small gamma is going to be a low pass filter, and it's going to go down like that. High gamma it's also a low pass filter, but it's less of a low pass filter. It'll respond more to the high frequency components. So you can think of gamma, the learning rate, as tuning the response to frequency components in the function that you're trying to learn. And that's an important thing. And that's just and again, I'll come back to this theme over time. Machine learning algorithms are low pass filters, right? All learning is low pass filters. The whole point is you take lots of experience from the past and you use it to make a prediction for the future. That lots of experience means that you're looking at a lot of data. How much data you look at is going to depend how far into the past you look. A slower learning rate means you're going to look further into the past. I learn less from each sample that comes in, and I'm going to have a longer memory for things in the past. It's still a fading memory over time, but it's a memory now nonetheless. Right? Whereas if I have a faster learning rate, I will be able to learn much more quickly, but I'm going to bounce around with things that are current. And this comes back to a little bit of when we're talking about overfitting and the idea of the minimum description length, the same kind of concept. It's when you're looking at time series data, the time series, how much do you fit? I have a time series coming in like this, right? Do I just fit everything there, or do I try to fit the little details of the time series? And sometimes one makes sense and sometimes the other makes sense, right? It depends on the time scale. So the gamma learning rate it's not there's a right answer. When you set fixed gamma learning rates, then it's going to depend on what kind of time scale you want to look over. But the point is to remember, no matter what you do, it's a low pass filter. It's not a high pass filter. There's no learning algorithm that says whatever I learned before, what does a high pass filter look like, right? It's something that says keep changing as much as possible, right? Whatever I learned before is definitely wrong. Let's learn something different. Oh my God, I just learned something. Let's learn something different. There are no learning algorithms that are high pass filters, right? There are learning algorithms that have second order behavior. If you look at the Laplace transform here, this is the first order. It's a first order filter. You can imagine second order filters. Second order filters are going to have terms that depend on the second derivative of W with respect to time. And those second derivative operator, that comes in very rarely, but sometimes people want that when you're looking at dynamic behavior. Just a terminology issue that I want to be clear about, the difference between adaptation and learning. I'm using learning in the machine learning sense. In the world of biological systems, there's no such thing as forgetting. Learning is permanent. Learning means you learn a skill. You can never, if you learn to ride a bicycle, you cannot forget to ride a bicycle, but you can adapt to changes in the bicycle's weight or size. And the point of adaptation is you can de-adapt, right? So you can, if there's a parameter change, you will follow it and you'll track back. So really what we're talking about is machine adaptation algorithms or low pass filters, right? But we tend to call it machine learning just because that's where it is. But just keep the terminology in mind is a little bit different. Let me stop there. And as usual, I will hang around for a bit. If people have questions, does anyone have any questions? Questions now you'd like to ask me?